Hello students, welcome to lecture 9 of the course Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on absorption, dispersion and scattering of light. So here is the lecture outline. As you can see, we will cover the absorption of light and provide a quick recap of the dispersion relation. We will also understand the effect of dispersion of light, and then we will study the different scattering phenomena which are named as Rayleigh scattering, Mie scattering and Raman scattering. So here is a picture of Lord Rayleigh, after whom this Rayleigh scattering has been named. So he was an English physicist and a Nobel laureate of 1904 who made a number of contributions to the wave physics of sound and optics. He formulated the theory of scattering of light by small particles and the dependence of scattering on 1 over lambda to the power 4. Okay. So, in a paper in 1899, he provided a clear explanation why we see the sky as blue. Okay. So, that was the first explanation of why sky is blue. You can imagine his contribution towards science. Okay. Meanwhile, Ludwig Lorentz, almost around the same time and independently, he also formulated the scattering of waves from small dielectric particles, although his research was published in a Danish in 1890. Okay. So these are the two gentlemen who have contributed really significantly to understand how light is scattered by different tiny particles. So let us try to understand about the absorption of light. So why light gets absorbed and who absorbs light. Okay. So till now we have seen dielectric media which are completely transparent, that means they do not absorb light. But is it really true? Now if you see glass, it is a material which is transparent in the visible spectrum. However, it is absorptive in the ultraviolet and infrared range. So it is something like the property, absorption property of any material is basically wavelength dependent. So at a particular range it may be completely transparent, but at certain other wavelength range it may absorb that light. And when a material absorbs light, what happens? So light will propagate through that material, will become attenuated. So this is how the amplitude of the electric field of the light will gradually reduce. Okay. So as you can see, the positive amplitude and the negative amplitude, they are reducing as the light is propagating along the z direction. So what happens in absorption? There is loss in the power of the propagating electromagnetic wave, and this is mainly due to the conversion of light energy into some other energy form. You all know that overall energy is conserved. So light is losing energy, it means the energy is getting transferred elsewhere, where it can go as lattice vibration, that is heat in the material. Okay, and that happens due to polarization of molecules of the medium or during the local vibrations of impurity ions driven by optical field. So these are two different phenomena that could be responsible for the loss of this energy of light when it propagates through a lossy dielectric medium. Now we adopt a phenomenological approach to the absorption of light in linear media. So let us consider a complex electric susceptibility corresponding to a complex electric permittivity, which is given by epsilon equals epsilon naught. Epsilon naught is the vacuum permittivity times 1 plus chi. Chi is the electric susceptibility, and a complex relative permittivity. So relative permittivity, it is basically epsilon r, that is epsilon over epsilon naught, and that is nothing but, from this you can find out, it is nothing but 1 plus chi. And here we have assumed that the electric susceptibility has got a real part and the imaginary part, okay, because the material is lossy. Now for any monochromatic light, we have seen that the Helmholtz equation for the complex amplitude UR remains valid. So, what will be the Helmholtz equation? You can write as del square u plus k square u equals 0, just that in such a medium, it's a lossy medium. So, k, the wave number, will now become a complex valued. It means it will have a real part and also an imaginary part. So, you can write k equals omega. Usually what you write, k naught, that is the wave number in vacuum, is nothing but omega, the angular frequency, over c, that is the speed of light. That is what you write in free space. Now, in this particular medium, k will be written as omega square root epsilon mu naught. Okay. Now, what is epsilon? Epsilon is basically epsilon r times epsilon naught. So, under the square root you will have square root of epsilon r times, you can write square root epsilon naught mu naught. So, that particular term can be written as c, because c is nothing but 1 over square root of epsilon naught mu naught. So, you can actually find that you are actually having k naught here, and the remaining term is epsilon r, which is 1 plus chi. So, if you express chi in its real and imaginary part, you will get 1 plus chi prime plus j chi double prime. Okay. So, now we understood that the wave number itself has become a complex. It has got a real part as well as a imaginary part. Fine. Now, while writing the k in terms of real part and imaginary part, we can introduce two parameters. One is beta, the propagation constant or phase constant, and alpha, which is basically the attenuation constant. So, if you write k equals beta minus j alpha by 2, I will tell you why this half factor is introduced later on, but let us assume that we are expressing the wave number, complex wave number, in this particular form. So, this can be related to this equation. It means beta and alpha can be related to the susceptibility components, which is chi prime and chi double prime. So, when you equate these two, how do you equate? Very simple. The real part should correspond to the real part, the imaginary part should correspond to the imaginary part, and once you do that, you can find out what is beta and alpha. Okay. Now, as a result of this imaginary part of the wave vector k, a plane wave with complex amplitude. So, this is a plane wave u that can have an amplitude a, that is exponentially decaying now, because k itself is lossy. Okay. So, it will have a change in the amplitude. So, you can write k as beta minus j alpha by 2. So, once you put this k here, you see it, you have got u equals a exponential minus half alpha z times exponential minus j beta z. So, this is the oscillating factor. Okay. Exponential j omega or j theta is basically the oscillation factor. Okay. And this is basically the decay factor of the amplitude. So, you can see the amplitude is decaying with a factor of alpha by 2. So, now if alpha is considered to be positive, you say this is basically a medium with absorption, and you will see that the envelope of A of the original wave. So, this is the envelope. Envelope is created by connecting all the peaks or all the dips. Okay. You can also have this one connected, all the valleys, you will get the envelope. So, you will see that the envelope is attenuated with a factor of exponential minus half alpha z. So, what is happening to the intensity? Intensity will be square of this factor, and so you will get exponential minus alpha z. So, this 2 gets into this one, you will get exponential minus alpha z. It means the intensity of an electromagnetic wave in a lossy medium will decay as exponential minus alpha z. Now, do you understand why we assumed half factor in the amplitude decay? Because we could get a intensity decay in the form of alpha z. So, this coefficient alpha is recognized as absorption coefficient. It is also called as attenuation coefficient. Fine. So, this is again the distance from peak to peak is called lambda. If you also take the distance from dip to dip, that is also the wavelength lambda in that particular medium. So, the simple exponential decay formula for the intensity actually provides the rationale why we choose the imaginary part of k to be minus alpha by 2. And let us look into the other parameter, which is beta. The parameter beta is nothing but the rate at which phase changes with z. It means it also provides the propagation constant of the wave. So, the medium therefore will have a refractive index, effective index, which is n. Okay. You can also call it n tilde, and that is given as beta equals n k naught. Okay. And the wave travels with a phase velocity Vp given by c naught over this particular effective index. So, that is the velocity of the phase velocity of the wave. Okay. Why we are considered about only phase velocity here? Because we assumed a monochromatic light in the beginning. Now, here you can see that we can find the relationship between this refractive index n, which is basically a complex number, and the absorption coefficient alpha, okay, to the real part of the susceptibility and the imaginary part of the susceptibility, which are chi prime and chi double prime. So, how it works? So, this n is basically a n tilde, that is the complex refractive index. So, that can be written as the real refractive index minus j alpha by 2 by k naught, and this is nothing but now square root of epsilon r, that is epsilon over epsilon naught. This can be written as 1 plus chi prime plus j chi double prime. So, once you equate the real part with real part, imaginary part with imaginary part, you will find each of these components, and that can be done easily for a weak absorbing media. In that case, you can assume that chi prime and chi prime, both chi double prime, both values are much smaller than 1. So, in that case, the square root can be approximated as 1 plus chi prime plus j chi double prime whole to the power half. So, you can bring that half in the front, okay, like a Taylor series expansion, and then you can correlate that this n is nothing but this real part, which is 1 plus chi prime by 2, and alpha, this part will be now same as this one. Okay. So, you can write that minus alpha by 2 k naught is basically half chi double prime. So, from that you can find out that alpha is basically k naught chi double prime. So, and there is a minus sign. So, minus k naught chi double prime. Okay. What is k naught? Again, k naught is basically the wave number in free space. So, this is how you can actually find out the relationship between the refractive index and the absorption coefficient in a lossy dielectric medium from the electric susceptibility, which is actually having real and imaginary components. Now, let us have a quick recap at the dispersion relation that we have already seen in lecture 6. So, this is basically telling you that if you assume this as the direction of wave propagation, so here we have assumed that the wave propagates along z direction, that means the direction for the k vector is along z. Electric field is oscillating along x plane and magnetic field is lying along y plane. Okay. We have seen that dispersion relation is basically the relationship between omega and k. So, we have known that omega equal Ck, or you can write C equals omega by k. You can also write C equals f lambda. Okay. These are few handy equations you must always remember. Omega you always know, omega is the angular frequency, that is 2 pi f, f is the linear frequency. F is nothing but 1 over the time interval, okay, of one period, okay, and k can also be obtained from 2 pi over lambda. So, these are the different handy equations for interchanging the values between linear frequency, angular frequency, time interval, and wavelength, wave number, and all these things. Now, in the presence of dispersion, we have seen that if the wave is not monochromatic, okay, the wave velocity will no longer be uniquely defined. It means it will have phase velocity for every frequency component, and as a group, as a packet, it will move with a velocity of group velocity that is given as Vg. So, one example is shown here, that you have, say you have a not a monochromatic light, rather you have frequency components something like omega plus delta omega and omega minus delta omega. So, when they add up, they actually form this kind of slowly varying envelope. So, in that case, this envelope is basically the envelope of the electric field maximum. Okay, if you connect all the peaks, you will get this. Okay, here also you get the peak. This is the envelope for the dip. Okay, so this is the wave packet, and the velocity with which this wave packet is traveling, that is the group velocity, that is dou omega over dou k. Whereas the individual frequency component will go along this path. Okay, and that is the phase velocity omega by k. We have discussed this in details, but reason why we are discussing it again here, to tell you that the dispersive media, okay, the media which has shown dispersion, can be characterized by a frequency dependent, or you can say wavelength dependent susceptibility. So, the chi is basically function of lambda, and hence the electric permittivity becomes function of lambda, also the refractive index and the speed. So, everything becomes function of lambda. So, that effect we have seen couple of times before, or even from our school days we have studied that the angle of refraction in Snell's law basically depends on the refractive index. Now, in a dispersive media, okay, it is the angle of refraction, or you can say the refractive index is angle dependent, sorry, it is wavelength dependent. So, if you make optical components from dispersive material such as prisms or lenses, you can bend light of different wavelength to different angles. So, that is what is happening. So, you can see this particular material, the glass material, can have a different, it has a different refractive index for blue, green and red. Okay, it means n lambda is different. So, if n lambda is different, then the speed of light in glass for different wavelength will also be different. The speed is given by v, okay, that is basically the phase velocity, c by n. Okay, so n lambda is different, so the velocity is different. So, that way the angle at which they will bend will also be different. Okay, so that is how you are able to get this kind of wavelength resolving capability of the refracting surfaces. You can also obtain wavelength dependent focusing power of the lenses, okay, based on this particular properties. So, what is crucial here is to remember that in dispersive media, the refractive index is a function of lambda, then the electric permittivity is a function of lambda, susceptibility is a function of lambda. So, there is not flat, okay, the value. If somebody asks you that what is the refractive index of this material, immediately the question you should ask back is at what wavelength you are talking about, because the wavelength is very critical here. So, a polychromatic light, it means chromatic means different colors, poly means many colors, monochromatic means single color, chromatic means color. Okay. So, polychromatic light is therefore refractive into range of directions depending on their different speeds of the different wavelengths. Now, by virtue of the frequency dependent speed, or you can say the wavelength dependent speed of light in dispersive medium, each frequency components comprising a short pulse of light experience a different time delay. Now, let us take an example here. Say we have a original pulse like this, and then we insert this pulse in a dispersive media, which can be a optical fiber. Okay. So, when it propagates through this dispersive media, you will see that the red light, okay, red light is having lower frequency or higher frequency. So, it has got longer wavelength or lower frequency. So, the low frequency component, it basically travels faster, and the high frequency component or shorter wavelength, they travel slower. So, the red light will reach earlier and blue light will reach later. So, this pulse will actually get broadened. So, the pulse gets delayed and broadened due to this dispersion effect. Okay. So, this is the important message that I wanted to pass here, because we will not discuss more about the pulse broadening and other effects associated with optical fiber communication. The main objective here is to tell you about the fact that refractive index, permittivity, these are wavelength dependent in a dispersive medium. Now, let us move on to the third topic that we are going to cover today, that is scattering of light. Now, what is scattering? So, when an optical wave travelling in a particular direction in a homogeneous medium encounters an object with different optical property, the wave is basically scattered or redirected into other directions. So, when a light beam propagates in a medium in which there are small particles or inhomogeneities, such as local changes in the refractive index of the medium, then some power of the beam is radiated away from the actual direction of propagation, and that means some power is actually getting scattered. So, scattering is basically a process in which some of the power in a propagating electromagnetic wave is redirected as secondary electromagnetic waves in different direction which are away from the original direction of propagation. So, there are number of different number of scattering processes, then they can be classified in terms of the size of the scattering particles in relation to the wavelength of the light that is being scattered. So, first in the list will be Rayleigh scattering. So, Rayleigh scattering is basically the case when the scattering particle size or the scale of the inhomogeneity in a medium is much smaller than the wavelength of light. And when we say much smaller, okay, that is typically lambda by 10. Okay. So, Rayleigh scattering involves polarization of a small dielectric particle or a region as shown here, that is much smaller than the wavelength of light. The field, the incident electric field of the electromagnetic wave, okay, forces dipole oscillations in the particle, hence it is getting polarized, and because the field is oscillating, the dipole will also oscillate, and an oscillating dipole radiates. So, that way this radiation will go out in all direction as scattered wave. So, what you will see that the through wave is actually reduced in the intensity, because some portion of the energy is basically scattered away by this dielectric particle, which is much smaller than the wavelength of light. So, the net effect is that the incident wave is partially re-radiated in different direction, and hence there is loss of intensity in the propagation direction. And we have assumed this particle to be small enough that there is no spatial variation through the particle. It means the field on the surface of the particle sees no variation. Okay. So, that is the case, we can assume that there is homogeneity in the electric field that is on the particle. We assumed a small particle, so that at any time the field has no spatial variation through the particle, whose polarization then oscillates with the electric field oscillation. So, whenever the size of the scattering region, whether it is a inhomogeneity or a small particle or a molecule or a defect in a crystal, is typically very much smaller than the wavelength of light, we call that process as Rayleigh scattering. And as I mentioned earlier, that it is typically smaller than 1/10 of the wavelength, okay, that you have to remember. Now, what is the intensity of the scattered light that Rayleigh has found out in his important paper, that the intensity is proportional to 1 over lambda to the power 4. So, that way you can understand that if you take blue light which has got shorter wavelength, so blue light will have the largest scattering intensity. So, it will get more scattered as compared to red light, which is having much longer wavelength. Okay. So, if you put the values of the wavelength on paper, you will see that the blue light, which is roughly 0.4 micron, will be scattered 16 times more than red light or infrared light, which is having a wavelength of 0.8 micrometer. Okay? And that is the reason why you have studied in your school days that ambulance and other danger signals, they have this red light, because it will get scattered less by the air molecules and the light can propagate the longest distance. Similarly, Rayleigh also explained, as I told, why sky looks blue. So, the scattering of light by air molecules, water droplets or dust particles present in the atmosphere, okay, they all actually give us this blue color, because the blue color is scattered much more than the red color. So, everywhere you will be seeing blue color being scattered, and that is why when we look at the sky far away from the sun, it looks blue to us. Okay? And during sunrise and sunset, why sky appears red? The reason is, in that case, sun is at the horizon, and it has to, the sun ray has to travel the longest distance through the atmosphere before reaching us. So, that in that case you can assume that in that path the blue light is getting scattered in all other direction, and only red light, which has got the lowest amount of scattering, is able to reach us, and that is why you can see the sky as red during sunrise and sunset. Another interesting thing is that the long wavelengths, something like orange and red, gives us the red color at this particular time. So, that is how the basic natural phenomena was explained by Lord Rayleigh based on his theory. So, the intensity of a light beam in a medium which has got small particles decreases as the light beam propagates through this particular medium due to Rayleigh scattering. And how do you quantify this particular loss of intensity? You can write that I, that is the intensity, is basically I naught, which is the incident light's intensity, exponential minus alpha r times z. So, what is alpha r? Alpha r is nothing but the Rayleigh attenuation constant, or you can say it is the attenuation constant due to Rayleigh scattering, and times z. So, with distance the intensity decays. So, if this material with Rayleigh scattering elements are longer, so you will have more decay along the path. Okay? And what are the factors that decide this alpha r? So, alpha r basically depends on the concentration of the scattering particles, capital N, the size, it means the radius a, then the wavelength of the light that has been incident, and the mismatch between the refractive index of the scattering spheres and the index n naught of the medium. So, what will be the difference? That will also appear here in this particular term. So, that will decide what is the attenuation constant for this Rayleigh scattering. Now, when the particles slightly get bigger, in the sense when the dimensions of the scatterers are comparable or greater than the wavelength of light, it is described by Mie theory, and we call that as Mie scattering. And we will not go into the details of Mie theory. Mie was also able to explain in 1908 the different colors of colloidal solutions of different nanoparticles, okay, based on his theory. So, as a picture is showing here, that if this is the direction of light propagation, whenever you have Rayleigh scattering is more like omnidirectional, it happens in all direction. Mie scattering is more like mostly towards the forward direction, and it becomes more directed towards forward direction if the particles grow in size. So, what are the example of the elements which are involved in Mie scattering? They are basically long organic molecules in solution, or they can be different particulate pollutants, as in smog in the atmosphere, including the dust particles. Okay. So, the scattering depends on the ratio of the scattering particle diameter to the wavelength of light, and it favors scattering in forward direction. So, this is one thing that is particular or peculiar about Mie scattering, is that in Rayleigh scattering it was more or less omnidirectional, but Mie scattering is more or less, it favors forward direction. Okay. So, what are the other factors? That the dependence of the wavelength in case of Mie scattering is weaker, okay, than compared to Rayleigh scattering. It means here the result for red, blue and green wavelength will not be that dramatically different. Okay. And the scatterers are assumed to have a refractive index significantly different from that of the surrounding medium. So, here there are the difference between n and n naught is significantly large. You can assume that if this is a metallic nanoparticle or any other nanoparticle, surrounding is air. So, there is a drastic difference. Okay. And Mie scattering also produces almost white glare around the sun when a lot of particulate material is present. That is like dust particles which are much larger or comparable to the wavelength of light. Okay. And this is also the reason why we get white light from mist or fog. So, all the colors they get mixed up, and that is why you get the white glare. Okay. The reason here is given, this is happening because Mie scattering, the dependence of wavelength is not that strong and dramatic as in Rayleigh scattering. Okay. And the last most important scattering feature, there are also different types of scattering, we will not discuss about those, but this particular scattering, also known as Raman scattering, is very, very important. Okay. So, let us look into what kind of scattering is called Raman scattering. Now, when light encounters a molecule in air, the predominant mode of scattering is basically elastic scattering. Now, when I say elastic scattering, so you can take this example that incident light is having an energy of E naught. Okay. And when the scattered light is also having the same energy, we call it as elastic scattering, where the momentum is conserved. Okay. However, it is also possible that for the incident photon to interact with the molecule, okay, in such a way that the energy is either gained or lost in this process, so that the scattered photons will have some shift in their frequency. So, they may have a higher energy, so they may get blue shifted in energy, or blue is having higher energy or lower wavelength, or they have lower energy, okay, than the incident photon. It means they can get red shifted in wavelength. So, this kind of scattering is called inelastic scattering, while the momentum is not conserved, because there is energy exchange with the molecule and the light. Okay. So, inelastic scattering is called Raman scattering. So, or we can say Raman scattering is an example of inelastic scattering. So, the photons from the laser beam interact with the molecules and excites the electrons in them. The excited electrons are in a virtual state which is not stable, so they immediately fall down to the ground level. And as the electrons lose energy and fall to the ground level, they emit photons. So, there are three scenarios of how light can be re-emitted after the energy has been absorbed by an electron. So, as you can see here, so this electron absorbed this incident light energy and it has gone to this high energy level or the virtual level. Now, if it comes back to the same ground level, then it is a elastic scattering, that is you can call it a Rayleigh scattered light. Okay, means this one. Now, there are possibilities that the excited electron may not come down to the ground level, rather it will come down to some intermediate vibrational level, something like here. So, in this case, if it comes down to a energy level which is higher than the ground level, in that case the Raman scattering will have a lower energy. So, we can call this as Stokes Raman scatterer. There could be the other possibility also, that the electron has actually gone from this vibrational level to the excited level, but while coming back the electron has jumped down to the ground level. It means this energy, it has actually given up a higher energy. Okay. In that case you are giving a larger energy of the scattered photon. So, that is basically anti-Stokes-Raman scattering. So, here also we can actually show it with the same examples, but in a different representation, as you can see here. So, if the electron falls down to the original ground state and there is no energy exchange with the molecule, so it means the same wavelength of light will get emitted or scattered. This is called Rayleigh scattering. Now, the second case, after being excited, so from here the electron is excited to the higher energy state, it falls to a vibrational level like here or here, same thing. Okay. It means in that case the molecule that is involved has absorbed some energy. So, the emitted photon has got some lower energy or longer wavelength. So, the red color is showing that. Red color means longer wavelength, blue color means shorter wavelength. So, this is called Stokes scattering. The other possibility, as I mentioned, that the electron initially was in a vibrational state and it got excited to a upper state, okay, and from there, or virtual level, from there it has jumped down. Okay. In that case, the emitted photon will have a larger energy, means shorter wavelength. So, this blue color corresponds to that. So, these two cases are called as Stokes scattering and anti-Stokes scattering. Both are Raman scattering and they are also inelastic scattering because the momentum is not conserved here, right. So, that is all for today. So, we will start discussion about electromagnetic waves in periodic structure in our next lecture. In case you have any queries or doubt, you can drop an email to this particular email address, but make sure you mention MOOC on the subject line. Thank you.